In this section, we will be looking at mass spectrometry. Mass spectrometry, or MS, measures the mass of particles, which could be either atoms, molecules, or fragments of molecules. Mass spectrometers typically consist of an ion source where the analytes are ionized, then a mass analyzer where these ions are then separated according to their mass to charge ratio, and a detector where the abundance of each ion with a different mass to charge ratio will be measured. The first step in mass spectrometry is ionization. The atoms would first be ionized by knocking off electrons, and usually only one electron would be knocked off to form a positive ion. Most of the time, an ion with a charge of +1 would be formed. This applies even to atoms that you usually won't think would form positive ions. For example, Cl, chlorine. Typically, you would think that they form chloride ions, Cl-, but in mass spectrometry, one electron would be knocked off, so it forms Cl+. So I've just written this as an example. The chlorine atom can lose an electron to form chlorine plus. After the atoms are ionized, the ions are then accelerated before they reach this tube, which is curved. Next, a magnetic field is applied to the path of the ions. The magnetic field causes the ions to be deflected from their straight path. The amount of deflection would then depend on their mass to charge ratio. Lighter ions will be deflected more. As an illustration, let's say you have a small ping pong ball, which is very light, and a tennis ball, which is much heavier, traveling along a path. And in the middle, you put a fan. The ping pong ball, which is lighter, would be deflected much more compared to the tennis ball, which is heavier. So similarly, ions which have a lighter mass will be deflected more compared to ions that have a heavier mass. Ions with a greater charge will be deflected more. For example, an ion could be formed with a charge of +1 or with a charge of +2. The ion with the charge of +2 will be deflected more. Now, how do we calculate the mass to charge ratio? Let's say an atom of carbon-12 loses one electron to form C+, then the mass to charge ratio would be 12, which is the atomic mass of carbon-12, divided by 1, which would be 12. Now let's say an atom of carbon-12 loses 2 electrons to form C2+. Then the mass to charge ratio would be 12, which is the atomic mass, divided by 2, which is the charge. And so the mass to charge ratio would be 6. If we take a look at the ions A, B, and C, we can see that the ions are deflected to different extents based on their mass to charge ratio. Some of the ions will collide with the walls, and only ions with a particular mass to charge ratio would make it to the detector. By varying the magnetic field, the ions with different mass to charge ratios can be selected to reach the detector. Finally, when the ions reach the detector, it would give rise to an electrical signal. This is what a mass spectrum looks like. We see a graph with lines on the graph. So the y-axis is the relative abundance or intensity. So ions that have a higher abundance would have a higher line. The x-axis is the mass to charge ratio. So in this mass spectrum, we can see that there are ions with mass to charge ratios of 92, 94, 95, 96, 97, 98, and 100. The most abundant ion is the one with mass to charge ratio of 98. We can tell that it is the most abundant because it has the highest peak. In this first example, we are looking at the mass spectrum of an element. This is a mass spectrum of molybdenum, which is an element. Now, since it's an element, you may wonder, why are there so many peaks? Well, each peak represents a different isotope. So based on the mass spectrum, Assuming that all these ions have a charge of 1, molybdenum consists of 7 different isotopes with atomic masses of 92, 94, 95, 96, 97, 98, and 100. Next, let's look at the mass spectrum of an organic molecule. This is a simplified mass spectrum of pentane. We can see that the mass spectrum of a molecule has even more peaks compared to the mass spectrum of an element. So besides isotopes, what else can give rise to these different peaks? In molecules, each peak would represent a different fragment that is produced when the molecule breaks up. So if we remember the processes that happen during mass spectrometry, the first step is ionization. During ionization, the vaporized organic sample would be bombarded by a stream of electrons. Well, if you happen to read up further, you may find out that there are actually different methods of ionization, but this method is actually a very common method used. It is called electron ionization. So basically, the atoms or molecules in the sample are bombarded with a stream of electrons to knock off an electron from the atom or molecule. So in the case of an organic molecule, an electron will be knocked off to form a positive ion. This ion would be known as the molecular ion or the parent ion. After ionization, this ion can then break up into smaller fragments, which would have smaller mass to charge ratios. So this gives rise to the different peaks on the mass spectrum. Let's take a look at the molecular fragmentation of pentane, for example. After ionization, pentane would form this molecular ion. Since one electron has been removed, it has a positive charge, and you will also see a dot here which represents a free radical. A free radical means that this molecule contains an unpaired electron. We know that usually in molecules, the electrons will exist in pairs, either bond pairs or lone pairs. But in this case, since one electron has been removed, there is one electron which is unpaired. The molecular ion can further fragment. So these are some examples of how it can fragment. When it breaks down into two pieces, one of them would carry a charge, so that would be an ion, and the other piece would just be a free radical without any charge. The fragments that do not have any charge will not be detected on the mass spectrum, whereas the ions that have a charge would be detected on the mass spectrum. In this example, we have ions with a mass to charge ratio of 29, 43, 57. This can be detected on the mass spectrum. The molecular ion itself has a mass to charge ratio of 72, and we can also see it on the mass spectrum. Theoretically, there should be one more with a mass to charge of 15, but I'm not sure why it's not appearing on the mass spectrum. Perhaps it's just not so stable, so it is not as likely to be formed. So on the mass spectrum, the peak with the highest mass to charge ratio is due to the molecular ion, which is the ion that has not fragmented. The tallest peak on the mass spectrum would be called the base peak. The base peak is assigned an arbitrary height of 100, since the y-axis is actually relative abundance. The base peak would correspond to the most common fragment or the most stable ion. Earlier, we have already seen how pentane can be ionized and then further fragmented. So when we look at the mass spectrum, we are able to assign the peaks that we observe to the fragments or the ions that are formed. Now let's take a look at another example, which is the mass spectrum of pentanethreone. The chemical formula of pentanethreone is given here. I'll also draw it to make it a little bit clearer, hopefully. First, let's calculate the mass to charge ratio for the molecular ion. The molecular ion has 5 carbon atoms, 10 hydrogen atoms, and 1 oxygen atom. So we can confirm that the peak with a mass to charge ratio of 86 corresponds to the molecular ion. Now how about the peak with a mass to charge ratio of 57? If we look at the previous example for pentane, pentane also had a peak with mass to charge ratio of 57 and it was formed by this ion. But is this fragment possible for pentanethone? If we look at the chemical structure of pentanethone, we will see that it just cannot form this fragment. To find the different possible fragments, we can mentally chop bits and pieces off the molecule until we come up with something that adds up to 57. So for example, first we could try to chop off this CH3. That would give us a remaining fragment with a mass to charge ratio of 71. So that's not enough. Let's try chopping off the other CH2. If we calculate the masses of these atoms added together, it will give us 57. So this is probably the ion that gives rise to the peak at 57. Next, another possible fragment that can be formed is by chopping here, we have just CH3, CH2. If we add up the atomic masses, we would get 29. So the CH3, CH2 ion gives rise to that peak at 29. This slide summarizes the explanations for the mass spectrum in the previous slide. Mass spectrometry can be used by itself, or it can also be coupled with chromatography. If it is coupled with liquid chromatography, then the abbreviation would be LCMS, or if it is coupled with gas chromatography, then the abbreviation would be GCMS. These methods can be used to analyze mixtures. First, the chromatographic method will be used to separate the components in the mixture. Then each component is detected by mass spectrometry. Mass spectrometry will then give more information about the structure of that compound. A mass spectrum is able to provide information about the chemical structure of the compound. Nowadays, GCMS and LCMS instruments also come with a database of mass spectra. So when the sample is analyzed, the results can then be compared with the mass spectra of known compounds. This enables a quick and easy verification of that sample's structure and identity. Mass spectrometry is able to distinguish between very similar compounds. Here we can see the simplified mass spectrum of pentan 2-one versus the mass spectrum of pentan 3-one. These two compounds will fragment differently and therefore give rise to different mass spectra. As we have seen, mass spectrometry provides information about the chemical structure of compounds. So mass spectrometry itself can be used to confirm the identity or structure of drugs and raw materials. When mass spectrometry is combined with chromatographic methods like GCMS or LCMS, the method will be able to separate compounds in a mixture and identify them. So this provides a method to characterize impurities that could be present in drugs or formulation excipients. GCMS and LCMS can also be used to test for drugs and metabolites in biological fluids. Finally, let's take a look at the strengths and limitations of mass spectrometry. When combined with chromatographic separation, so that's LCMS or GCMS methods, the method is very useful to rapidly identify trace impurities. This is important because there is a limit to how much of certain impurities we can have in the drug. And as we know, certain impurities can even be carcinogenic. Besides the analysis of small molecules, MS can also be used for quality control of large molecules such as therapeutic antibodies and peptides. Techniques like GCMS and LCMS are also able to provide confirmatory identification of drugs. However, some limitations is that this instrumentation is expensive. It also requires support by highly trained staff and it requires regular maintenance.